polymers. One type of polymer is an addition polymer, and you did this for AS. An addition polymer is when the monomer is an alkene, contains a carbon-carbon double bond, is an alkene, and when an addition polymer is formed, no other product is made. It's just a polymer is made. Okay, a classic example of an addition polymer is when you take ethene, is the monomer, ethene, that is called the monomer, ethene. And if you take N of them, that's just a number, N, lots of them, and the carbon-carbon double bond breaks, the hydrogens are still there, and it forms two new bonds, and you draw brackets because that's the repeating unit, and N because it repeats lots of times, and that is poly, and you put the name in brackets of the monomer, polyethene, and that's the polymer. Now your monomer is unsaturated, got carbon-carbon double bonds, but your polymer is saturated, single carbon-carbon bonds. Okay, so it's the simplest example. Another type of polymer is a condensation polymer. Condensation polymer. And the definition of a condensation polymer is when monomers react together. When monomers react together, with the elimination of a small molecule e.g. water or HCl are very common examples. Okay, that's a condensation polymer, and there's three types of condensation polymer. Okay, there is polyesters, there is polyamide, and there is polypeptide proteins. Proteins are made up of polypeptides. Okay, so those are the three kinds of condensation polymer. So let's look specifically at each example, right? So if we take a polyester first, okay, now there's two ways to make a polyester. Okay, when you're making a polyester, which functional group is made? It's making an ester, right? So you can take a monomer like ethane 1,2-diol, okay, which has got an alcohol group at either end. Remember, to make a polyester, you need one of the monomers needs to be an alcohol, and one of the monomers needs to be a carboxylic acid. But because you want it to be a long chain, it needs to be a alcohol at either end and a carboxylic acid at either end. Now, a good tip when you're drawing polymers is to do everything in a straight line like this. It really helps you when you have tricky examples. You do everything in a horizontal like that, okay? So we've got a di-alcohol and we've got a di-carboxylic acid. Now when these react together, you know when you make an ester that there is a loss of water. But be very careful here. Remember, it is the H of the alcohol and the OH of the carboxylic acid when you're making an ester, because that lone pair comes in and attacks there, and like that. So it's the H from the alcohol and the OH from the carboxylic acid. And so the same thing would happen at this end as well, and similarly at that end as well. So when you're given a question, the first thing to do is work out where the water is going to be lost, okay? So we know that water is going to be made. So water is going to be made, right? And then here, at this end here, we have lost the hydrogen because that's joined with another carboxylic acid. So we lose the hydrogen, so we just leave an open line like that, CH2, CH2O. And this O has now joined with this C. And there's a benzene ring in the middle. And then this C, double bond O, and then it's just a line, because the OH will have formed with another alcohol, would have formed water. Okay, so then we put brackets round. The bonds have to go outside the brackets, and an N. Okay, so if we take N of the diols, and if we take N of the dicarboxylic acids, that will be our polymer. And can you see here, there's our ester group, and it's a polyester. And your ends, this is where you can lose marks. You've got to make sure the carboxylic acid end is a C double bond O, and the alcohol end is just the O like this. Okay, this is actually a well-known polyester. This has got the trade name Terylene, and it's used to make clothes. Okay, now this balanced chemical equation is not yet finished, because you've got N of the diols, N of the dicarboxylic acids. How many waters are going to be made? All right, so you can either remember how many waters, or you can work out how many waters. So if you take one monomer, and I'm going to call it a square, all right, and it's going to join with, this is the diol, and it's going to join, form a bond with another monomer, a different one, called a triangle. Okay, so if two monomers come together, that's going to make one water. Okay, N equals, there's one of that monomer and there's one of that monomer, so N equals 1. Right, but if you have that monomer joined to that monomer in a repeating, which is what we've got in a polyester, okay, so we have got 3 water molecules there. 3 water molecules are made when these monomers join together, and we've got 2 of each monomer. We've got 2 squares, we've got 2 triangles. And if you did this again, square, triangle, this is like the diol, this is like the dicarboxylic acid, and it's going like this, triangle, sorry, square, when we're up to triangle. Okay, so square, triangle, square, triangle, square, triangle. 1, 2, 3, 4, 5 waters will be released, because there's a water for every bond that's made, 5 waters, and there are 3 of each monomer. So what's the relationship between N and the water? Can you see what the relationship is? If we take 2N, 2N is 6, take away 1, that's how many waters are made. Try it here. 2 is M, 4 minus 1 is 3 waters. N is 1, 2 minus 1 is 1 water. So in these types of questions, when you have got a diol and a dicarboxylic acid, the amount of water that is made is 2N minus 1 water. 2N minus 1. Okay, that's a polyester. There's another way to make a polyester. Okay, exactly the same, just one polyester, exactly the same, but this time, polyester, again you need an alcohol and a carboxylic acid, just the same, but instead of having 2 separate monomers, we have a bifunctional monomer. So we have a monomer, so if we take this monomer has got a carboxylic acid and it's got an alcohol. Okay, this monomer is called 2-hydroxy propanoic acid. This monomer's got a common name, and the common name is lactic acid. Lactic acid is its common name. Right, so one monomer has got everything that you need. But again, that's going to be lost of the carboxylic acid when you're forming an ester, and that's going to be lost, the hydrogen's going to be lost there. So if we have N, lots of those, Then just make sure you draw it very carefully. CH3H, C. Okay, now the C double bond O, the OH is being lost, so it's just a line, brackets, and then the OH here, so it's O, but the H has been lost to form water, and that is your polymer, and that is the repeating unit. Oops, sorry, your repeating unit. Okay, plus water as well. How many waters are going to be made here? So if you have, there's only one monomer, right? So if you have one monomer joined to exactly the same monomer, okay, that's going to release one water. But N equals 2. Okay, because there's two monomers there. They're the same monomer, but there's two monomers. If you have another one, 3 squares, so there's N equals 3, there's 3 of them, and that releases 2 water. Can you see the relationship this time? This time it is N, take away 1 is the amount of water. So when you only have one monomer, it is N minus 1 waters. Okay, if I asked you to draw a section of this polymer with 2 repeating units, okay, so draw a section of this polymer with 2 repeating units, you would go, so draw it one time first, CH3H, C double bond O, so that's one time, and then that bond would be joined to the O, so you go O, and then you go C, CH3H, C double bond O, like that. And that's a section of the polymer with 2 repeating units. You don't go putting any ends in or anything like that. Now that's the polyester. Let's go polyamide. Right, very similar. To make a polyamide, which functional groups do you need? You need a carboxylic acid, but this time you need an amine. Okay, right here I've got a classic example here. If we take this amine, and I'm going to draw all the main parts on a straight line, CH2 6N, that's the amine, 1,6 hexane diamine. Okay, and then if we take this one here, so we're going to go, sorry, CH2 4. This one here, sorry, is called hexane 1,6 diamine. Okay, so we've got a carboxylic acid at either end, that monomer, amine at either end, very similar. It forms water. When the two of them join together, the OH on the carboxylic acid is lost as water, and the H on the amine is lost as water. So when it joins together, we've got because we're drawing the repeating unit, then you've got 6 carbons, then you've got NH. Now that N is going to be joined to the C, CH2 4, then C double bond O, and like that. Okay, and that is the repeating unit. That is the amide group. Amide group. Okay, we need N of those. We need N of those monomers, N of those monomers, N of those monomers, and therefore we need water as well. And because there are 2 different types of monomers, the number of water is 2N minus 1 water. And that's to make a polyamide. This is a well-known polyamide. This polyamide is called nylon. 6,6. It's called 6,6 because nylon, one monomer has got 6 carbons and the other monomer has got 6 carbons as well. It's used for clothing and ropes. Clothing and ropes. Okay, so just like with the polyester, there are 2 ways to make a polyamide. You either have diamine or dicarboxylic acid, or you have it all in one molecule. So you could have a molecule which has got a carboxylic acid and an amine, but exactly the same idea. You have N of those. When it joins together, you'd have bond N, that's where your bracket is, H, CH2, C double bond O, bond bracket M. Okay, plus there's only one type of monomer, so it's M-1 water. Okay, and that's a polyamide, which is very similar to a polyester. Okay, so last section is polypeptides and polypeptides, which are used to make proteins. Okay, now these are really similar. A peptide group is very similar to an amide group. It looks like that. It's exactly the same as an amide group, amide peptide. The only difference is that polypeptides, the monomers are amino acids. Okay, but the same, the actual group itself, the functional group, looks exactly the same. Okay, so it's amino acids. So if, for example, if you took this amino acid, which is called glycine, and if you took this amino acid, which is the next simplest amino acid, CH3, H, C double bond OH, which is called alanine. Okay, and if those two join together with a loss of water, okay, we just take one of them and one of them, just one, not poly, just one, and then you've got glycine, and that C double bond O is joined to that N, H, C. Be careful with connectivity. I'm writing it at a funny angle. Okay, that plus one water. Okay, that is called a dipeptide because it's got made from glycine and then alanine. It's a dipeptide because it's made from just 2 amino acids. Okay, you can't draw an equation for a polypeptide because there's lots of amino acids and they're all random. So instead they give you a section of a polypeptide. But before I go on, if you have a tripeptide will be, dipeptide is 2 amino acids, a tripeptide is 3 amino acids. Okay, if I give you a section, have I got a section here? Let's give a section of an amino acid, not amino acid, sorry, a section of a polypeptide. All right, you can't draw an equation for it because there are different amino acids. So I've got one here, benzene ring, okay, and then etc. Okay, so there's a section of a polymer. I can't put N, and I shouldn't have put brackets. Let's remove the brackets because I shouldn't have put brackets. And there's 2 different amino acids there. Okay, so a polypeptide is lots of different amino acids joined together. If you take, finally, if you take a section of polymer, okay, let's take a section of polyamide. A section of polyamide. And I've said that, and now I've drawn a section of polyester, but hey, let's take a section of polyester instead. How do you break up, not polyamide, polyester, how do you break up a polyester and a polyamide as well? So you need to break the ester bond. So to break the ester bond, there's two ways. You can do acid hydrolysis, or you can do base hydrolysis in order to break an ester link. Alright, so if we did acid hydrolysis on this section of polyester, okay, then we would end up back with a carboxylic acid, we'd end up back up with the carboxylic acid, and we'd end up back up with the alcohol. Okay, if we did base hydrolysis, and we'd be a bit more accurate, if we say sodium hydroxide, base hydrolysis, then what would you end up then if you did base hydrolysis and you break this bond here? Remember, it's that bond of the ester you're breaking. What would you get if you did base hydrolysis? Oops, benzene ring's gone rubbish. Would you get a carboxylic acid if you do base hydrolysis? No, you'd get the sodium salt. O minus Na plus. You get the sodium salt. You still get the alcohol as well. Okay, and similarly, if you were to take a polyamide, which is what I was going to do originally, you take a polyamide and you do acid and base hydrolysis on a polyamide. So let's take a polyamide here. Let's go C, C double bond O. Okay, just taking the. It doesn't matter what we do. Just got a polyamide there. Polyamide. We do acid hydrolysis. We reflux it in acid, or just warm it. To be honest, it'll happen if you just warm it. And in sodium hydroxide. Okay, what we're going to be, you're going to break just the same. You're going to break that bond there, that's the most important bond of the amide, and you would end up with a carboxylic acid, the dicarboxylic acid, and the amine. But would you get the amine if you've done acid hydrolysis? Would you get the amine? No, because it's an acid, so you'd have to put another hydrogen on, positive charge, and it'd be Cl minus, Cl minus, okay? And similarly, sodium hydroxide, you wouldn't get the carboxylic acid, you would get the sodium salt. Sodium salt, my handwriting has gone, completely gone. O minus Na plus, and you'd get the amine as well. CH2, 6, NH2.